Hi, my name is Hannah Ryan, and this video is on the periodic table. In this video, I'm going to explain the differences between periods and groups. I'm also going to go over electron configuration as it relates to valence electrons and oxidation numbers. So I'm going to be able to show you how to determine how many valence electrons an atom has, as well as how to predict an oxidation number for an atom. I'm also going to go over the differences between metals and nonmetals, and also I'm going to show you how to locate metals and nonmetals and metalloids on the periodic table. I'm going to show you some important groups you should know, such as the halogens, noble gases, alkali metals, and alkaline metals. And most importantly, I'm going to teach you the trends on the periodic table and why the trends are what they are. And I think that's a really important component of this. So I hope you learn a lot from this video, and I hope you enjoy it as well. First thing we're going to talk about in this video is the difference between a group and a period. A group is, as you can see, a vertical column on a periodic table, and a period is a horizontal row. And I have that written over here so you can copy it down if you need to. Alright, we also need to look at what is so important about groups. Well, each element within a group has similar properties with other elements in that group. Also the same number of valence electrons and the same oxidation number as other elements in that group. So I'm going to explain this in greater detail by explaining electron configuration and the components that go into electron configuration, and hopefully that will help you all determine how many valence electrons each element has, and also what oxidation number to predict for an element. And it will just give you an overall better understanding of the periodic table itself. So that is my next topic I'm going to talk about on this video. Okay, so I'm going to talk about what quantum numbers are, because I think quantum numbers will give you a better understanding of the trends that I'm going to talk about later, and it will also help you understand what your electron configurations that you've been writing actually mean. And I'm also going to go review, after I review the quantum numbers, how to write electron configuration, just to make sure that you know how before we move on to the trends later on. Okay, so the first quantum number is N, and N is actually the energy level that this element you're configuring is on. And so I just gave an example. Here's something you'd be configuring, and it'd be 3s1. So the N would be 3. N equals 3. Some third energy level. And that means as you go down on a periodic table, let me find a periodic table really quick. Should have one. There we go. Alright, as you go down a periodic table, you get more electrons because you go down energy levels, and if the atomic number equals the amount of protons and electrons, then lithium with an atomic number of 3 has 3 electrons, and as you go down in that group, rubidium has 37. And it's also, lithium would have an energy level of 2, right here, and rubidium would have an energy level of 5. So as you can see, this is important to remember that you have more electrons the further you go down a group. The further you go, the higher your energy level is, the more electrons you have. That's important to understand. Okay, so our N equals 3. Now L is another quantum number, and L is defined as between 0 and N minus 1. So you can, if the highest energy level is 7, then L can range from 0 to 6. But if N equals, for the highest energy level, L can range from there. We usually don't go past, we usually don't go past 3. So this one would be from 0 to 2, right? Because N minus 1 would be 2. And this is actually what L is, this letter. L is represented as a letter, because L also represents the shape, and so you think of the letters as the shapes as well, and it's just a way to write it in electron configuration. Just a way to write it where you can tell all the characteristics of this element. So this is our L in this case, and S is 0, P is 1, D is 2, and F is 3, and that's as far as we're going to go. But in this case, these are the levels that this energy level can have. Now, it's important to understand that a sublevel will not exist unless the atom has at least enough electrons to occupy parts of the sublevel. Okay, what does that mean? Well, lithium and oxygen, if you can look at your own periodic table, are on the same energy level of 2. Well, sublevels, we know, here's the S, here's the P on this side. Okay, well, lithium only has 3 electrons, so it is not going to make it to the P sublevel, even though on the second energy level you can have from 0 to 1, which means you could have an S and a P sublevel. Okay, so that means that even though you're on the same energy level, you may not have the same amount of sublevels. It all just depends on how many electrons you have. So you have to actually write out your electron configuration and determine if you have enough electrons to have a certain sublevel. Okay. Alright, so within each sublevel, you can have 1 or more orbitals. And an orbital is defined as a region of space with a high electron density, and each orbital can have a maximum of 2 electrons. One will be spinning in one direction and one will be spinning in the other. If you've written your full electron configuration, then in each box, when you write out arrows like that, that is an orbital. And within each sublevel, like that would be the P sublevel. And within each energy level, let's say, that could be one energy level. That could be like, pretend the 2, N equals 2. So we have energy level, sublevels, and orbitals. Does that make sense? Okay. So this is a chart that can help you just condense the information you just learned. If your quantum number L is 0, the letter you would use to represent it is S. You would have 1 orbital, a total of 2 electrons, because in each orbital you have 2 electrons. And as you go down, you can see the trend grows. Okay. There's one more quantum number to go over, and that's the magnetic quantum number. And all you need to know about the magnetic quantum number is that it ranges from negative L to positive L. That's all you need to know right now about the magnetic quantum number. Oh, and another important thing I do not want you to forget when you are writing your electron configurations, especially when you write the expanded form with the orbital showing, is that electrons fill orbitals with the lowest energy first. Okay, so I want you to go ahead on your paper and try to write the electron configuration for sodium. And I'm going to do it at the same time. I'm going to use my periodic table, and I'm going to look for sodium. So I would say that I have 1s2, 2s2, 2p6, 3s1. And then I'm at sodium. So let's just go ahead and look at sodium to determine, and look at the electron configuration of sodium to determine some characteristics of this element. Well, what's its highest energy level? 3. N equals 3. Right? Okay. Well, let's also decide what sublevels it can have. Well, if you look at 3, that means that L could be from 0 to 2, right? So L can be anywhere from 0 to 2. And then we have to look at the number of electrons that sodium has. And obviously from our electron configuration and from our letters, we don't even have to do that. We just realize that it can only go to the S and P because it doesn't have enough electrons to make it down to the 3D level. Okay. So that's right. Oh, and two other things we need to determine, we need to go over, are how many valence electrons sodium has. We also need to determine the oxidation number of sodium. First, we need to talk about what valence electrons are. Valence electrons are the electrons on the outermost shell of an atom. And valence electrons are a big deal when we talk about reactivity of elements. So it's important to understand it's important to be able to determine how many valence electrons an element has. So to determine how many valence electrons an element has, you only look at the P and the S energy levels. And you look for the highest P and S energy levels. That is how you should remember how to determine the valence electrons. So here our highest energy level is N equals 3. And there's no P and there's just an S. And then you look at the exponent it's raised to. In this case it's 1. There's only one electron in the S. And that's the highest energy level. So we only have one valence electron. Okay, now we need to go over oxidation number, what an oxidation number is. And how I can predict oxidation number by looking at valence electrons and looking at where sodium is on the periodic table. Well, first of all, sodium is a metal. Second of all, it only has one valence electron, as I just determined. Now, a full valence shell would be 8 valence electrons. The noble gases over here have 8. The goal is to get to a full outer shell because that makes an element the most stable, the least reactive, because it doesn't need any more electrons to fill its shell. It is full and it doesn't need to react. And that is the ultimate goal. Okay? Well, would it be easier for sodium to gain 7 electrons or to lose that 1? That's right, lose that 1 electron. Now that electron is a negative. That's why I write electrons like this to help me remember. It's E negative. So if sodium loses its 1 valence electron to have a full outer shell, its oxidation charge is going to be a +1 because it lost that negative. It started at 0 and you subtracted a -1. So its oxidation number is going to be a +1. Oh, okay. And since sodium has a +1 charge, and since each element within a group has the same oxidation number and number of valence electrons, we can therefore assume that lithium, potassium, rubidium, cesium, and every other element in group 1 metals has 1 valence electron and an oxidation number of +1. Super brilliant. Get it on the periodic table, and first you have hydrogen and helium, so it's 1s2, and we have 2s2, and that's it. Then you're at beryllium. So, first thing we need to do is look for the highest energy level, because that's the number of valence electrons you're going to have, and that would be 2, and we only have S, but S has 2 electrons in its orbital, so we have 2 valence electrons. That means every element in that group has 2 valence electrons. Now, it would still be easiest to lose those 2 valence electrons. So we have, it had an oxidation number of 0 minus the -2 electrons. We're going to have a charge of +2. That's most common. So every element in the group 2 metals has a +2 charge. Now, I'm just going to go ahead and tell you that boron has a +3 charge, as you could assume, because its valence electrons would be 2s 2,2,2,P1 for boron. Let's write it in the condensed version. It has the noble gas that was before it. That's how you write it in the condensed version. You write the noble gas that came before it, and then you write the rest of it out, which would symbolize its valence electrons. And since these are the highest energy levels, those are the valence electrons, and S and P, and S has 2 and P has 1, so we have a total of 3. It's still easiest to lose those 3, so it has a +3 charge. And that would be for the entire group of boron. And carbon, it's in the middle, so it can have a plus or minus 4. We're just going to go ahead and show you that. Now, I'm going to show you one example from the nonmetals so that you can see where they get their negative oxidation number. But then I'm going to go ahead and tell you the other oxidation numbers for the nonmetals, because once you know one, you can catch up on the trend and be able to predict the others, and that's what I want you to understand. So, I'll do chlorine. Let's do the full. Chlorine has an electron configuration of 1s2, 2s2, 2p6, 3s2, and 3p5. So what we want to do is, for valence electrons, we're only concerned with the highest energy level. So we have 3. So we have 2 electrons here and 5 here, so we have a total of 7 valence electrons. I'm going to say it would be much easier to gain 1 electron than to lose 7, right? Okay, so chlorine's ultimate goal is to gain that negative electron. Okay, so it had a charge of 0, and then we gained a negative electron. So our charge is going to be -1. Okay. So every element in that group, which is the halogens, has 7 valence electrons with an oxidation number of -1. Now, on the periodic table, we're going to say that the nitrogen group has 5 valence electrons, and it's easiest for them to gain 3 electrons rather than lose 5. So it's going to have a -3 charge, every element in that group. We can already pick up on this trend, can't we? The oxygen group has 6 valence electrons, and it is easiest for them to gain 2 more. So they're going to have a -2 charge. Okay, and we already described what the halogens would have, and the noble gases already have 8. So yes, their oxidation number is 0 because they don't need to lose any, they don't need to gain any electrons. They have their full shell. So the noble gases are unreactive with an oxidation number of 0. So to sum this up, valence electrons are the electrons on the outermost shell of an atom, and if you're going to use electron configuration to determine how many valence electrons an element has, you need to just use the S and P sublevels, and you need to use the S and P sublevels where N is the greatest. So your number out in front of the S and P is the greatest because that's your highest energy level, so it's going to be the furthest outside the atom, because really the atom is structured like this. You have your positively charged nucleus, and then here's each energy level. So as you go up in energy levels, you gain more electrons around these rings, and then at the very end, the outermost shell contains the valence electrons. Okay? So the next thing we're going to talk about is the differences between nonmetals and metals. So I'm going to go back to using screnium to show you on a periodic table where the nonmetals and where the metals are, and I'm going to describe some properties of each, and also I think I will tell you the trends for reactivity as related to metals and nonmetals and the groups of each. Okay, so I have put up a periodic table, and it has shaded in blue for metals, pink for metalloids, and yellow for nonmetals. So if you want to label that on your own periodic table so that you can use it to refer back to, then that is fine. Go ahead. And now I'm going to give you some properties of metals. Metals have a shiny luster, they're malleable, they're good conductors of heat and electricity, and they tend to form cations in aqueous solutions, which is a positive charge. And we've already talked about metals having an oxidation number that is positive. So that's where we get that they tend to form cations in aqueous solutions. So those are the blue shaded in elements, are the metals. Okay, the nonmetals are yellow, in yellow on this periodic table, and they do not have a luster. The solids are usually brittle, some are hard and some are soft. They are poor conductors of heat and electricity. They tend to form anions in aqueous solutions, which makes sense with the negative oxidation number to form negative charges in solutions. Anions are negative, and their melting points are lower than that of metals. And metalloids in the pink are just intermediate between metals and nonmetals. Their properties are in between the two. Also, it is important to understand that metallic character increases as you move towards francium on a periodic table. So as you go down and across, metallic character increases, which makes sense. Least metallic up here, most metallic down here. So least metallic here, most metallic here. Alright. It's also important to understand that the A groups are 1, 2, 3, 4, 5, 6, 7, 8, where I pointed with the mouse. So hydrogen, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and helium. Those groups all have, they're all the A groups in 1 through 8. But they can also be known as 1, 2, and then over here 13 through 18. If you include the transitions. But more commonly, the transitions will be the B groups, transition metals. And so that would be 3B, 4B, 5B, 6B, 7B. And then all three of these are 8B, and then 1B and 2B again. And they can also be known as groups 3 through 12, and this will be 1, 2, 3, 12 over here. But more commonly, like I said, they're known as the A and B groups. Group 1A contains the alkali metals. Group 2A contains the alkaline metals. Group 7A over here contains the halogens. And Group 8A contains the noble gases. So those are the most important ones that you must memorize. Next, I'm going to explain to you why reactivity increases as you go down a group for metals, but it decreases as you go down a group for nonmetals. Okay, so I'm going to explain why reactivity increases as you go down within a group for metals. The first thing I want to remind you of is that metals want to lose electrons. So as you go down a group, it must get easier for them to lose electrons if they are becoming more reactive, right? But why? Why is it easier for them to lose electrons as you go down within a group? Well, there are two main things that you must understand, and that one would be shielding electrons. Now, this is a model of lithium, and this is rubidium, as you can see. Now, lithium, as you all know, or should know, is a lot higher than rubidium within group 1. And as I said earlier, as you go down energy levels, you gain more electrons. Well, rubidium is down a lot more energy levels than lithium. And it is shown by these two diagrams that rubidium has a lot more shielding electrons. All of these electrons that are in between the positively charged nucleus and the negative valence electron are shielding. Well, this one only has 2 shielding electrons because it only has 2 energy levels, and the second energy level is actually where the valence electron is. See this positively charged nucleus? Well, that positively charged nucleus has a pretty good grasp on that one valence electron because there's not very many shielding electrons blocking that pull. Rubidium has a lot more shielding electrons, so the effect the nucleus has on the outer electrons is lessened by these core electrons, these shielding electrons. So you have all these negative charges, and so the positive's pulling on those, so the effect it has on this last one over here is weakened. And that's why lithium actually has the stronger hold on its outer electrons, its nucleus does, than rubidium's. And it also has to do with size. Look how much closer this nucleus is to the outside electron than this one is. So, if metals want to lose their valence electrons, well, rubidium could lose its valence electron a lot easier than lithium, couldn't it? Yes. So that is why reactivity increases for metals as you go down a periodic table, and that is why it would decrease for nonmetals. If nonmetals want to gain electrons, then they're going to have a harder time if that nucleus does not have as much of an effect on those outer electrons. So it's reversed. In nonmetals, they don't want to lose them. They want a strong hold on their outer electrons, and they want an even stronger hold so they can pull more in. Let's say it was fluorine, it would be more reactive than, let's say, bromine, if you look on your periodic table, because it's the reverse. Fluorine is smaller, so its nucleus has a more powerful effect on those electrons. It can hold them in. So bromine wouldn't be able to as well because it has more shielding electrons and it's larger. And I have a video that I want to show you that I think will help you understand or just visualize what happens to, this is the group 1 metals, what happens as you go down the periodic table, just how much more reactive they get. So this video will just show you, it starts with lithium and it goes down to cesium, and you will just really be able to see how how much more reactive these metals get as you go down within a group. So here we go.
Whether you've left school or you're still at school, you can appreciate the sheer fun and mayhem that chemistry can be. There's so much to it. Bunsen burners, mixing chemicals. Very nice. Now, you may have been allowed to mix very small amounts of lithium with water. You may, if with a responsible adult, have mixed H2O with sodium. And you may, under very strict scientific control, have witnessed potassium mixed with water. But the odds are, if you have, it will only ever have been on one of those rubbish science videos. There you go, mate, present. These next two are the dog's nuts of the periodic table. They are, if you like, the king and queen of alkaline metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody. This one's going to be bad.
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone. Wow. That is more like it. Only on Brainiac do you get that kind of science. But I believe we can go one better. There is one more alkali metal we can legally use.
Yes, Richard, cesium, the emperor of alkali metals, particularly nasty to go off at any time.
And that's it.
Oh, yes.
Brilliant. I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in a bathtub.
Fair enough, mate. I'll leave you to it. Good luck.
Thank you.
Okay, John, go for it.
Warning, 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 extreme danger, clear the area.
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. And it does. Magnificent. And I think that concludes today's experiment. There is, I should say, one more, even more reactive metal, francium. But for some reason, they wouldn't let us have any of that. So, there you go. Today's lesson.
Never mixed alkali metals with water.
Okay, so I hope that helped you really see how much more reactive obviously cesium is than, let's say, lithium, because it's so much easier for it to give up its electron. And that is why the reactivity increases for metals as you go down the periodic table, but it decreases for nonmetals because nonmetals, remember, want to gain, not lose. Okay. The atomic radius is the size of an atom, and it increases as you go down within a group. It also increases as you go across to your left. So this will be the biggest, smallest. Okay, but why? Why does the size change in those directions? Well, I have a very good way to explain this. And it's effective nuclear charge and also shielding. But you have to know when to use which one. Effective nuclear charge is best to use when you're going across a period. So we'll talk about that first. This is a symbol for effective nuclear charge. So you can write it in your notes. And basically what it's saying is you're not going down any energy levels when you go across a period, right? You are just gaining more protons and electrons. Well, my Barron's book has a good explanation for this, and here it is. Of the atoms in a period, each succeeding atom has an additional electron and an additional proton. The electrons are added to the same shell and are located at a relatively constant distance from the nucleus, with a slight increase in atomic radius due to the electrons repelling each other. However, the increasing nuclear charge is a stronger effect, and this increase in effective nuclear charge attracts electron clouds closer to the nucleus, decreasing the overall radius. In atoms within... So, basically what that was saying was that as you go this way within a period, you are gaining the same amount of protons as electrons. You're gaining one proton, one electron each time. And that electron will make it a little bigger because they're repelling each other. However, that effect is not as strong as that proton's effect in that positively charged nucleus, and that's known as the effective nuclear charge. So as you move to your right, you are gaining more protons. Those protons have a greater pull on those valence electrons, making it smaller. So that's why as you go to the left, it gets larger because you have less protons, and so the effective nuclear charge is not as strong as it is to the right. So that is a very good way to explain why this trend is the way it is, and I use it all the time. Alright, but that explains why it shifts as you go across a period, but what about when you go down and up a group? Why does it get bigger as you go down a group? Well, I already explained to you what shielding electrons were, and that's pretty much it, and the energy levels. So you could just think of it as you go down, there's more energy levels, so it's larger. There's more shielding electrons in those energy levels, so that nucleus does not have as strong of a hold on those outer electrons. It's larger because it cannot pull them as closely, and therefore it's larger as you go down within a group. So that explains atomic radius. Now, we also have to discuss what ionic radius is. Okay. Ionic radius is when there's cations and anions involved, like the oxidation numbers, like when those are involved. So, a good way to remember it is that anions are always larger than the element. While cations are always smaller than the element. Alrighty, but why? Why again? We need to understand this. Why are cations always smaller and anions always larger? Well, what is a cation? Something that lost an electron. Alright, well, if a cation loses an electron, or more than one electron, it's due to the fact that it now has more protons than it does electrons. So those protons have an even greater hold on those electrons than before, so it gets smaller. Now, but why are anions greater in size than the actual element? Well, my Barron's book has another good explanation for this. It's kind of complicated. All you really need to know is that anions are greater than the element, but if you want a little bit of an explanation, go ahead and listen to this. Anions are always larger than neutral atoms. Many are almost twice the size. Since the added electrons go into the same shell, the gain in electrons does not fully explain the increase in size observed. Chemists reason that the outer electrons in an atom effectively shield each other from the nuclear charge. This shielding decreases the attractive forces and the size of the electron cloud expands, resulting in the large anion radius. So the electrons that are in the outer shell actually shield each other, so the more you get, the more they are shielded from that nuclear charge, so the larger it gets. Now I'm going to give some examples, and you're going to have to put these elements in order of increasing or decreasing atomic radius. I'll let you know which one, and then I'll give you the answers. So these are just some to try. Here are some practice problems on atomic and ionic radius, and the first one says rank the following elements by increasing atomic radius: sulfur, oxygen, neon, and aluminum. So go ahead and think about what the right order would be, from smallest to largest. You can pause this and try to figure this out. I'm going to go ahead and give you the answer. Neon, and then oxygen, and then sulfur and aluminum. Aluminum being the largest, neon the smallest. So go ahead and go back, and if you can't remember, if you got that wrong, think about why it could be what I put by thinking about effective nuclear charge and shielding electrons. Don't just try to memorize where the arrows are pointing, where it's getting bigger. Just think about effective nuclear charge and shielding, and that will help you understand these trends. Alrighty. So the next one is rank the following elements by decreasing atomic radius. And we have sulfur, fluorine, sodium, rubidium, and phosphorus. So go ahead and try that one. And remember, it's decreasing atomic radius. So I want the largest one first. Rubidium is the largest one. Whoa. Rubidium's the largest. Sodium is next. Then we have phosphorus, sulfur, and finally fluorine. Fluorine's the smallest because it's over the furthest to the right, so it has the most protons pulling on it for the size that it is. And it has the least amount of shielding electrons, it's the smallest. So, okay. The next question is, which of the following has a smaller radius? The chlorine or chlorine ion or the same? Let's go ahead and think about that one. Well, what's the chlorine ion? The chlorine ion is Cl minus, right? So it's an anion. And what did we say about anions? Anions are greater than their element in size. Anions are greater in size than their actual element. Therefore, which one's smaller? The actual element, not the ion. So chlorine, A would be correct. So there are 3 more trends we need to talk about before I'm through with this video. And the first is ionization energy, and that is the energy required to remove an electron from an atom. And the trend is that ionization energy decreases as you go this way. It increases, obviously, as you go to the top right corner. So lowest is right here, highest ionization energy is here. Now let's think of this in terms of affecting nuclear charge and shielding. Well, francium at the bottom has the lowest ionization energy because it is easiest to remove an electron. It doesn't require as much energy as fluorine to remove an electron, near as much, because it is huge. It has a ton of shielding electrons, so it's very easy to give up that electron, one of those valence electrons. And fluorine is at the very top of the group and all the way across the period, so it is much smaller. It takes a lot of energy to remove an electron from fluorine. Fluorine wants to gain electrons, not lose electrons, remember? So that explains why it wants to gain them and not lose them. It is so small that its nucleus is pulling its outer electrons in very tightly, and it's hard to remove an electron. The next trend is electron affinity, and that is the energy change that accompanies the addition of an electron to an atom. And this basically means that like some atoms readily attract electrons, and so the electron affinity has a negative value, and that means that energy is released. If they readily attract electrons, like fluorine and chlorine, they would readily attract electrons because they're pulling those electrons in. It doesn't require really much energy. It requires energy to remove electrons, but not to gain them. It's naturally pulling those electrons in. So the electron affinity, it has a very high electron affinity, and it explains that it means that it's going to have a negative value for the electron affinity because energy is released. Most, however, do not accept additional electrons readily, and the electron affinity is a positive value, indicating that energy must be used to add the electron. Fluorine has the highest electron affinity for electrons, and francium has the lowest. Electron affinity varies diagonally across the periodic table. So the atoms close to fluorine tend to accept electrons readily, and those close to francium do not. So again, this time the highest electron affinity is here, and the lowest is down here. Okay, and last but not least is electronegativity. And electronegativity describes the attraction of electrons by individual atoms. And it's kind of a combination of ionization energy and electron affinity, and it shows that it's a trend of just how well they can attract electrons. So, of course, fluorine can attract electrons way better than francium can. It's got a a much higher electronegativity because it's trying to attract, while over here we are trying to lose electrons. So electronegativity increases up and over to the right. Again, just go across the periodic table. So that is pretty much everything that I need to go over about the periodic table. I hope you enjoyed my videos, and I hope you learned a lot and have a better understanding of the periodic table.